Okay, so when you think black hole, what pops into your head? Probably this single, massive, terrifying void in space, right? Well, what if I told you that what we call a black hole isn't just one thing? Not at all. Get ready because we're about to meet an entire cosmic family. For decades, this has been the iconic image, a single point of infinite density with gravity so unbelievably strong that nothing, not even light, can escape. It's like the ultimate cosmic vacuum cleaner. And, it's an idea that's both completely terrifying and weirdly captivating, something we started imagining over 200 years ago and that Einstein's theories really brought to life. But here's where it gets really, really interesting. That simple, monolithic idea, that's just the start of the story. The reality, hidden in the solutions to Einstein's equations, shows us there are actually four fundamental types of black holes. You can think of them as four siblings in a cosmic family, and each one has its own unique personality. So, if they're a family, what makes them different? What's the cosmic DNA that defines each one? Well, it turns out to be surprisingly simple, and it all boils down to a concept with a truly fantastic name. And that concept is called the no-hair theorem. This theorem basically gives us the complete, and very short, recipe for building any black hole in the entire universe. The no-hair theorem it's beautifully simple. What it says is that once matter collapses to form a black hole, all of its complicated details, like was it made of hydrogen or iron, was it shaped like a star, or I don't know, a giant space teapot, all of that just gets wiped away. That complex information, which physicists whimsically call hair, is gone forever. Only three basic fundamental properties are left behind to tell its story. And here they are, the only three ingredients you need. First, mass. Pretty straightforward, right? How heavy is it? How much stuff is crammed in there? Second, its net electric charge. And third, its angular momentum, which is really just a fancy way of asking, how fast is it spinning? And that's it. Seriously. Mass, charge, and spin. Every single black hole that could possibly exist is just some combination of these three things. Okay, so let's play Cosmic Chef for a minute. If we start mixing and matching these three ingredients, we can build the entire black hole family tree. This table lays it all out for us. It's the complete family portrait. So first up, you've got the short-shield black hole. This one only has mass, no charge, no spin. It's your basic, no-frills, classic model. Okay, now let's add a little something. Let's give it some electric charge. Boom, you've got a Reisner-Nordstrom black hole. Now what if we go back to that basic model and add spin instead of charge? Well, that gives you the Kerr black hole. And since pretty much everything in the universe spins, this is probably the most common type we'd actually find out there. And finally, you've got the whole shebang, the Kerr-Newman. It's got mass, it's got charge, and it's got spin. It's the most complete, most general version of a black hole possible. All right, let's zoom in a bit because things get seriously weird when you add spin to the mix. We're going to take a little trip deep inside the most common type, that Kerr black hole, just to see how unbelievably bizarre its internal structure really is. Just look at this comparison. A simple, non-rotating short-shield black hole is a perfect sphere. It's got one event horizon, the point of no return, and a single infinitely dense point at its very center. But a rotating Kerr black hole? Oh, that's a whole different beast. It's flattened at the poles, kind of like the Earth is. It has not one, but two event horizons. And its singularity? It's not a point at all. It's a ring. And this just illustrates that bizarre structure perfectly. It's not a simple point. It's more like a cosmic onion with all these different layers. What we're looking at here is a map of a place where our everyday understanding of space and time just completely falls apart. So let's take a tour, shall we? Layer by layer. First, you'd fall into something called the ergosphere. In here, space-time itself is being dragged around by the black hole's spin so violently that you literally can't stand still. You have to move with the rotation. Then you'd cross the outer horizon. That's the classic point of no return we all know. But inside a Kerr black hole, the journey's not over. Next, you hit an inner horizon, a weird second boundary. And then at the very center, you find it. The ring singularity, a one-dimensional ring of infinite density. Now here's the absolute kicker. According to the math, because the singularity is a ring and not a point, you could theoretically pass right through the middle of it. You could fly through the hole in the donut, so to speak, without getting crushed. The equations suggest you could actually avoid the singularity and pop out the other side, maybe even into another region of spacetime. It is an absolutely mind-bending possibility, and it comes straight from the physics. Of course, we can't exactly send a probe to check this out. So how on earth do physicists even begin to picture a place like this? Well, they use these extraordinary theoretical maps. This isn't a physical map, obviously. It's called a Penrose diagram. It's a kind of conceptual map of space-time that squishes infinite distances and times down into a single finite picture we can look at. And the one for a Kerr black hole is incredibly complex. I mean, look at this. It labels our universe, sure, but it also hints at these pathways to an anti-gravity universe, or even another universe on the other side of that ring singularity. This is a map of pure mathematical possibility. So Einstein's theory of general relativity gives us this totally wild, counterintuitive family of black holes and these bizarre maps of what's inside. But the theory itself breaks down right at the singularity. It just can't describe that ring of infinite density. To really understand what happens at the very edge of reality, we're going to need a new theory, one that finally unites gravity with quantum mechanics. And that is the next great frontier in physics. Just imagine what secrets are waiting for us there.